Welcome to section 12.3, inference about two population proportions. This time we're doing dependent samples. So in chapter 11 we did independent samples. Now we're doing dependent samples. We're going to be doing something called McNemar's test to use this. McNemar's test. And let's look at an example using dependent samples, which again could be called matched pairs data. So a recent general social survey asked the following two questions of a random sample of 1,483 adult Americans under the hypothetical scenario that the government suspected that a terrorist act was about to happen. So two questions. Do you believe the authorities should have the right to tap people's telephone conversations? Do you believe the authorities should have the right to detain people for as long as they want without putting them on trial? And the results are shown below. So these people are being matched up against themselves, right? However they answered one question and compared to however they answered the other question. And we're organizing this with this contingency table. So for instance, these people right here, 224 people disagreed that authorities should have the right to tap people's telephone conversations, but they agreed that they should have the right to detain people as long as they want. Okay? So our claim that we're testing for McNemar's test is always the same. And do the proportions that agree with each scenario differ significantly? And there's our level of significance. So, for instance, we're looking at this proportion, everyone who agrees, versus this proportion, everyone who agrees with tapping your phone. All right, so again, we're going to look at the proportions, everyone who agrees with detaining indefinitely, and everyone who agrees with tapping the phone. All right, so let's look at our approach. So the sample proportion of individuals who believe that the authorities should have the right to tap phones is, so tap phones, we did that in green, so it's 572 plus 237. I'll just do that actually up here. So 572 plus 237 is 809. So out of 1,483 people, 809 agreed that you could tap the phone. And we want to know if this is significantly different to the proportion of individuals who believe the authorities should have the right to detain people. So that was 572 plus 224. 796 people out of the sample agreed it was okay to detain people. Okay, so there's a natural difference, right? Looks like there's a difference of about 13. So we would ask ourselves the question, is this difference due to sampling error, which could definitely happen, or is it significant enough to conclude that our proportions are really different? All right. So that's how we're going to be running our test. So in general, when we're setting up our dependent sampling for two proportions, we're going to set it up like this. Agree, disagree, we're going to generalize to success. Whoops, that's not a highlighter. Success and failure. So success is agree, failure is disagree. And normally our problem will define for you what is considered success. Our parameter is two proportions from dependent sampling. The hypothesis test is always the same for McNemar's test. You can consider it a two-tailed test, but we're on the chi-squared distribution, so it's going to have a different meaning. Don't use p-hat, remember. So the null is the proportions are the same. The alternative is that the proportions are different. All right, our assumptions is that our samples are dependent. dependent sampling method, obtained randomly. And this one's new for us. The total number of observations where the outcomes differ must be greater than or equal to 10. Okay, so what we're talking about in that one, where they differ means we get a success or failure. Excuse me, success and failure. So those are the two columns, or the two corners. So in this case, let's just double check. We can go up and look at our example. Where they differ is 224 and the 237. So those are definitely greater than or equal to 10. So we can run McNemar's test. And that is our test. And we don't actually have a calculator function for it per se. We can use chi-squared CDF later, but we're going to have to remember how to get the p-value. All right, our test statistic on the next page is this. It's on our chi-squared distribution. So let's go ahead and calculate that out. All right, so if you guys have worked with matrices before, they're using the same notation as matrix notation. So for instance, this F sub 1, 2, it's not 12, it's 1, 2. That means first row, second column. First row, second column. And likewise, this one down here, S sub 2, 1, that's the second row, first column. Okay, so that's how we're matching up our data. All right, and notice this, these are all the ones that, these are the values that are different, that differ. So agree and fail. Okay, so in our case, F of 1, 2, F sub 1, 2 is 237. F sub 2, 1 is 224. We're going to square that. And then we're going to add them together. All right, and then let's see what we get. We can type it in on our calculator. Remember your parentheses. And we get approximately 0.3666. We'll go out 4 decimal places. All right, so now essentially we want to know if this is considered unusual or not. So we have 2 ways to do that. We could do the classical approach using our chi-squared distribution. All right, we're always going to use degree of freedom 1 for McNemar's test. Here, I'll just draw our graph twice, degree of freedom 1. And our alpha was 0.05, so let's check out our critical value for our chi-squared distribution. Again, you can use your chi-squared distribution chart for this. And we're going to find that this is equal to 3.841. 3.841. And our test statistic is 3.666. So our test statistic is just barely in the OK zone. So this is not in the critical region. All right, so we know we're not going to reject the null. Over yonder, now we have our test statistic for the p-value approach. And for McNemar's test, we're going to calculate the area to the right of the test statistic. And again, with degree of freedom 1. So chi-squared CDF, 0.3666. We're going off to infinity. And degree of freedom is 1. And we're going to put that in our calculator, and we're going to get 0.5449. And again, compared to alpha, this is bigger than alpha. So again, that tells us not in the critical region. So again, we are not going to reject the null. So make our decision. Do not reject. And if we're not rejecting, it means we have insufficient evidence. At that alpha equals 0.05, level of significance. Forgot that part. To conclude that there is a difference in the proportion of adult Americans who believes that it's okay to phone tap versus detaining people for as long as they want without putting them on trial in the event that the government believed a terrorist plot was about to happen. Okay, so go ahead and try an example on your own. We're going to be using phantoms. Go ahead and push pause, and then come back and check your answers. All right, so here are your solutions. So again, these values are definitely different, but we want to know, are they significantly different? And notice we pick on the 31 and the 43 in our hypothesis test, because that's what makes those proportions different, right? So really, if there's going to be any sort of differences, it's the 31 and the 43, those values that are success and failure at the same time. Our hypothesis test is always the same for McNemar's test. Our assumptions are a little bit different. We want to make sure that the success and agrees are bigger than or equal to 10. We have our test statistic. And then the O in phantoms and the, well, we can obtain our p-value. And then at this point, you don't have to show both on the exam. You guys can either choose to do the classical approach or the p-value approach. But I do want the test statistic, obviously, and I also want the p-value. So give both, and then however you make your decision, that's fine. You don't have to do both. Again, classical approach, we look at our chi-squared distribution with degree freedom 1. Our p-value, we can look at chi-squared CDF, area to the right of our test statistic with degree of freedom 1. Both cases shows us the test statistic is not in the critical region, so we do not reject the null. So again, that means there's insufficient evidence to support the alternative.